morning, Matt. First student, exciting. Did you say you had your midterm yesterday or Monday? Does that mean you're all done? Good morning, Joey. Yay, exciting. Woohoo! Okay. It looks like most people have started the project. Homework 10 is so long. It's not... It's just long. It's long. Yeah, it is. It's long. The hardest thing is keeping everything straight. You really need to check your work at every single step. It's annoying and long. And the programming project it's challenging. It's meant to be challenging. The hardest part for the programming project, at least in my opinion, is translating your code or your equations into your code. Yeah. I don't know. One thing at a time. Keep pushing forward. In the homework, for the homework, yeah. So let me remember. So if you get something, like if you can't get B, the worst thing is you can solve it in MATLAB and use those answers. Just say like, I know I got the wrong answer, I'm moving forward with what I got from MATLAB. So like for problem 3, I think, you have to, so A, you just do your multiplication, x equals A inverse B. For part B, you have to find the A matrix, which means you need to find the inverse of the inverse. If you do all your row operations and you just banging your head against the wall, worst thing is you write down, this is what I should get. I use this function in MATLAB, and then move forward with that for part C. So you can do that if you want. It's not a bad plan. But these problems are long. They are so long. This is like, yeah, I know. I understand. I wrote the solution. I typed it all up. What I've done is I've legitimately checked my work at every single step with MATLAB. So, if you want to, like, I mean, in MATLAB, you just say, type in your A, type in your identity, whatever it is, and then you just check your work. You really, I mean, I wrote, I wrote a function that does my row operations. Yeah, that makes sense, JR. Sure, you can type the homework in a Word doc if you want. If you really want to. I'm not going to stop you. It does look neat when it's typed up. Make sure you're showing your work when you're typing it up. And have fun. It does sound painful, I'm not going to lie. It really does sound painful. But if you want to, that's fine. Just make sure it shows your work. But yeah, these problems are very, very long. This is definitely the longest linear algebra homework you'll have to do. We will do row operations again next week when we do LU factorization and PLU factorization, but there's less row operations to do. So it's not as frustrating, which is good. Yeah, in the past we've had the like programming project due at the same time as this homework, and students are like, there's way too much going on here. So we gave you guys some extra time for the project this year, which I think is good. And I think you think is good. So, okay. Yes. So the fundamental, like a row operation is not that bad, but there's so many places where you can make a little mistake, which is really frustrating, especially since like they concatenate. So if you make a mistake in like your second row operation, you don't really realize it until you get to the answer because MATLAB tells you that's not what you should get. And then you're sitting there like staring at the piece of paper thinking, where did I make a mistake? And then there's like a tiny sign error that you made in like your second row operation, and it affects all your other million row operations. Sometimes though, it does help to do all of your steps explicitly. So maybe you do want to show that row operation where you're just multiplying a row by a number. Maybe you do have some row operations. No, not Jib, I'm not extending it. I was talking about previous semesters versus this semester. Matt, junior level's hard. Junior level classes are hard. There's a lot there. Yes. Okay. So we can complain about row operations for a while, but let's go ahead and start class today, start lecture, and continue talking about determinants, which are less stressful. Or less. Okay, notes, there we go. Okay, so on Monday, we learned how to take determinants. So, we learned how to do cofactor expansion. There we go, we learned how to do cofactor expansion. We can do it along any row or any column. Typically, we want to pick the row or the column that has the most zeros, like in this 4x4 example. We picked column 1 because it had the most zeros, but you could pick any row or any column. You find all of your cofactors, which we will do again today, and then you take each element in that row, multiply it by the cofactor, and add it all together. We also learned quickly how to do our more or less modified fish method for a 3x3. So you should know how to do both ways. You'll be asked to do cofactor expansion in your homework. But if you prefer the fish method moving forward, then use the fish method moving forward. You still need to know how to find cofactors. One thing we did not get to on Monday is properties of determinants. And if I go to the notes, there's a whole bunch of properties of determinants. And most of the time, I don't really go over properties. They're like just fun things for, your knowledge to forget or look up later. But properties of determinants, we'll see these a couple different times, and they can be useful. So there's a bunch of them here. We've got properties of the transpose. So if you have a matrix and it's transposed, determinant doesn't change. These scenarios, so identical rows or identical columns, 0 rows, 0 columns, that's when our determinant is equal to 0. And I think I ran into an example of this in the other section on Monday. But anyway, if we ever end up with a row of zeros or 2 rows or columns, it works for rows and columns, then it's all zeros. And you can think about this in a sense of a 3x3, where if we end up with all zeros, then if we do our fish method, we'll see that every single diagonal has a 0 in it, which means you just have 0 minus 0. So we end up with all zeros. So if you ever run into MATLAB and you have an instance where your matrix tells you that it's singular, that means that you probably have a row of zeros when you shouldn't have one. Singular matrix means that it's not invertible, which means our determinant is equal to 0, which means that A inverse does not exist. And that's what singular means. That's all that fun stuff in MATLAB when it tells you that your matrix is singular or rank deficient. Typically that means you have a row of zeros, which affects our determinant. A rank deficient matrix would apply in a non-square matrix. Same thing with identical rows and identical columns. You can just do row operations and you'll get a row of zeros. Matrix product, if A and B are both matrices, then the determinant of A times B is equal to the determinant of A times the determinant of B. One main one, or one really interesting one, I guess one you'll see, a triangle matrix. So this is where you end up with your triangle of zeros. I'm really creative on the numbers today. If you ever end up with a triangle of zeros in any size matrix, it's just going to be this number times this number times this number. You just multiply along the diagonal. Once again, this makes sense with a 3 by 3. If we do our modified fish method. Along these ones, it's just 1 times 4 times 6 plus 0 plus 0. Same thing along this side. I lost a 0. Anyway, it's just along the diagonal. Did I do that right? I did. Anyway, so for a triangle matrix, our determinant is just the main diagonal multiplied by each other. The remaining 3 properties I want to point out are ones when we do row operations. So I have an example for this one. So here I have this A matrix. And let's say I am going to reduce this matrix until I get my Gauss elimination form, my row echelon form REF. Yeah, row echelon form REF. So I get my lower triangle of zeros. So if I start out with this A matrix here, first I say row 3 equals row 3 plus row 2. So I'm adding these 2 rows together to make a 0 here. Woohoo, did that. And then I'm saying row 1 equals 3 times row 1, and row 2 equals 4 times row 2, because I want to make sure these 2 numbers have the same and opposite. And I'm going to add those 2 rows together to get a 0 here. And then, just for fun kicks and giggles, I'm going to exchange these 2 rows. You don't have to, but for kicks and giggles, I'm going to do that, just as an illustration to show how the determinant changes. And then after I do that, I go ahead and do another 3rd row operation, or 3rd reduction operation to get my 3rd 0 here. Okay, so a couple things to note. Our row operations, we are going to multiply a row by a constant, so n times a row. This is our row operation 1. Row operation 2 is where we swap rows, so row 1 swapped with row 2, or row n swapped with row m. And our row operation 3, this is our elimination step. It's really important that we define what that is. So row operation 3 is where we're going to replace a row by adding the row to some non-zero multiple of another row. Okay. So this number here, this can be a number in front of my other row. This has to be a 1. You might do row operations where it's like row 1 equals 3 times row 1 plus 4 times row 2. This is not strictly row operation 3. This is a combination of row operation 1 and row operation 3, where you're saying first row 1 equals 3 times row 1, and then row 1 equals row 1 plus 4 times row 2. So when we're doing row operation 3, which it's important that we understand this for determinants, but also important that we understand this for next week's material, row operation 3 strictly needs to have the row we're replacing, you cannot multiply it by a constant. You need to have a 1 here in this location. So you're multiplying the row, the other row, by some non-zero constant. This one, the row you're replacing, cannot be multiplied by a number. So just clarifying that. Okay, so let's say, so this determinant here is equal to -1. I can go ahead and check that in MATLAB. Let me type it into MATLAB quickly. So A equals, ignore the other A, 4, -3, -3, -3, 5, -3, 3, -4, 1. Okay, so determinant of A is 1, or -1. So I'm going to start there, and we are going to see how our determinant changes as we go through all these row operations. Okay, so there's some principles that we... Some principles are determinant... Nope, wrong one. So our determinant properties, that's the word I'm looking for. Our determinant properties tell us that if we have row operation 1, we're going to multiply a row by a constant. Row operation, well, hold on. I want to keep this. So our determinant properties tell me that if I have row operation 1, where I multiply a row by a non-zero constant, then I'm going to multiply my determinant by that same constant. So for example, no, wrong one. For row operation 2, if I swap 2 rows, then my determinant changes sign. And if I do row operation 3, where I do my elimination step, then my determinant doesn't change. Okay, so I have those 3 options. I'm either multiplying my determinant by a constant, that same constant, I'm flipping the sign, or I'm leaving my determinant alone. Okay, so those are our 3 choices. So for this one, for this step, if I replace row 3 by adding row 3 to 2, for Gauss and Gauss-Jordan elimination, absolutely. You can combine row operation 1 and row operation 3. For Gauss-Jordan elimination and Gauss elimination, you have freedom to really apply these row operations in any way, shape, or form. You do not need to follow a specific pattern, but it is important that we understand the difference between all 3 of them. But in Gauss-Jordan elimination, you can combine them. You can choose whichever ones you want. That's completely fine. So this we have row operation 3, strict elimination step, which means our determinant doesn't change. So the determinant of this matrix here, where I used this one to make this a 0, should be -1, and it is. It should be -1. Okay, so great. This is row operation 3. Determinant doesn't change. When I get to this one, this is row operation 1. So row operation 3, row operation 1. I am replacing a row by multiplying a row by a constant, which means the determinant of this matrix is the same as this one, but multiplied by that constant as well. So the determinant of this one should be -3. I multiplied a row by 3, so I multiply my determinant by 3. Keep in mind, this is just for a single row. So if I have an entire matrix, remember that one's 0. Let's say I have this matrix. And let's pretend that my determinant is 1. If I multiply the entire matrix by a constant, so like 3, I would end up with this. To apply this property, I am multiplying row 1 by 3, row 2 by 3, and row 3 by 3. So I need to apply this property 3 times. So it's going to be 3 times 1, that multiplied by 3, and this multiplied by 3. So it's going to be 27. So you have to apply this for every single row. So this property is not for the entire matrix, it's just for a single row, or a single column, really. So if I multiply this row by 3, I multiply my determinant by 3. If I multiply this row by 3, I multiply that answer by 3. If I multiply this one by 3, then I multiply that one by 3. Okay, so keep in mind how you're applying these row operations, how you're applying these properties. Okay, so that's a nice fun aside. Back to our matrices over here. Okay, so then the next thing I did was I multiplied row 2 by a constant. So this is row operation 1 again. So if I multiply a row by a constant, that means I'm going to take my previous determinant and multiply that by that same constant. So it's 3 times 4, or negative 12. Okay, then I keep moving. So here I have row operation 3 again. This is my strict elimination. I'm replacing row 2 by adding row 2 to some multiple of row 1. So this doesn't change, so this one will also be negative 12. Here I have some row operation, or row swaps, so row operation 2. When you swap rows, your determinant stays the same, but the sign changes. So this becomes positive 12 now. And then lastly, here once again, so here is another strict elimination step, row operation 3. Note, row 2 is multiplied by a constant, but that doesn't matter because row 3 is not. So the fact that this is a 1 here, that makes it strictly a row operation 3. And for this one, the determinant doesn't change. So we can see how our row operations affect our determinant as we go along. So we went down. Let's go up. I'm going to erase all this fun stuff. And we're going to go backwards. If we look at this matrix here in REF, note this is a triangle matrix, which means our determinant is 12 times 1 times 1. So this here is easily 12. We can see that. Which means we can work our way back up. It's a little bit more complicated to work our way back up just because you have to think about the inverse. But we can see how it was affected as we go back up. Okay, so in this option, this here, we swapped rows, which means our determinant, am I muted? Okay. Which means our determinant changed sign. So if this one was positive 12, that means this one should have been negative 12. If we go back up again, this here is strictly row operation 3 because we take row 2 and we're replacing row 2 with some multiple of row 1. If we have just row operation 3, our determinant doesn't change. So if this one was negative 12, that means this one should have been negative 12. So row 2, those are the same. This doesn't matter if there's a number in here, it doesn't matter as long as these two, it's 1 and 1. Or 2 and 2, 3 and 3, whatever. Okay. So then we go back up again. So if we multiplied a row by 4 here, that means to undo it, we would divide our determinant by 4. So this would be negative 3. Same thing here. If we multiplied by 3 to do this row operation, that means to go back up, we would divide it by 3, so negative 1. And then once again, we have row operation 3, which means our determinant wouldn't change. So we can work our way back up. We can work our way back up. Essentially, I have it down one bit. This should be shifted up a little bit more. But we can work our way back up from the bottom by just undoing our row operations. So to go this way, we apply our determinant properties directly. To go the other way, we have to undo them. So it's essentially do the opposite, which it only really applies with row operation 1, where we're multiplying a row by a constant. So the negative one, I just calculated determinant directly. I use MATLAB to calculate this determinant directly. I said, hey, MATLAB, tell me the answer. Yep. Okay, so those are determinant properties. Ooh, sorry, trying to get hair off my screen. Those are determinant properties. They can be useful. Some of the more useful ones are the triangle matrix, where you just multiply the elements along the diagonal. It's really useful to do that. I'd say that's probably the most useful one, but it's important that you have all of these in the back of your mind and how they affect. You might be asked questions like we did here. Given REF, what is the determinant of your original matrix? So you can work your way back up through the row operations like we just did. Okay, so that's determinant properties. We've got 30 more minutes. Perfect. Okay, there we go. The last couple things to talk about in this, in this set of material is finding the adjoint matrix. It's finding the adjoint or adjunct matrix, which it turns out that the adjoint matrix is just a bunch of cofactors. So in order to find the adjoint matrix, what we're gonna do is we find the cofactors for all of the elements in the matrix. So we'll go over how to do that again. Then we put them all into a matrix and transpose it. So remember, all of this determinant stuff stems from the fact that the inverse of a matrix is 1 over the determinant times the adjoint matrix. So we know how to find the determinant now. There's lots of different ways to do it. We can do cofactor expansion along any row or any column. If we have a 3x3, we can do our modified fish method. We can technically apply row operations and get an REF in order to use a triangle matrix and work our way back up. There's lots of different properties we can use, but we can find our determinant. The second thing is to find our adjoint matrix, which, like I said, we're going to find the cofactors for all of the elements in our matrix and then plug everything into our equation. So let's look at this system of equations, and we are going to solve it. There's lots of different ways now we can solve a system. We can do substitution, we can do elimination directly on our equations. We can do Gauss elimination, Gauss-Jordan elimination, as you guys know, is very frustrating. We can find the inverse of a matrix using Gauss-Jordan elimination, which is the long way to do it. And now we have another way to find the inverse. So if I write this system in the form of AX equals B, so by the way, when in your homework it says matrix form, it means in AX equals B, where you write your A matrix, you write your X, you write your B, and then you apply matrix math. So if you know what X is, you can just say A times whatever your X vector is, 1, 2, 3. When you do that matrix multiplication, no, it's matrix multiplication. You take the dot product between the row and the column, the row and the column, the row and the column, all that fun stuff that you learned a while ago that you remember and you're like, oh, right, that was hard when I learned it. Now I've practiced it way too many times. But if you do that matrix multiplication, you should end up with your B vector, and you can compare your B vectors. And that's what it means by matrix form. Okay, so here I have this system in the form of AX equals B, and I know that my solution is X inverse times B. So to find A inverse, X equals A inverse B, yeah. It's 1 over the determinant of A times my adjoint matrix. And I know how to find the determinant. Let me go ahead and do that quickly. I'm going to use my modified fish method. So I take A, and I write it next to each other. do my diagonals. So this diagonal is 0. This diagonal is 12. This diagonal is 20. So add all those up, and I end up with 32. Then I go the other way. So this diagonal is 0. This diagonal is -6. This diagonal is -8. Add all those up, and I end up with -14. So I have 32 minus -14. It's going to give me 46. And if I look at my piece of paper, that is correct. So the determinant of A is equal to 46. Once again, there are multiple ways to find the determinant. This is my diagonal method, my modified fish method. Multiply these numbers, multiply these numbers, multiply these numbers, add them all together. 0 plus 12 plus 20 is 32. And then my other direction, multiply these numbers. Multiply these numbers, multiply these numbers, multiply these numbers. Add them together. 0 minus 6 minus 8 is -14. Then I take my main diagonal numbers minus my other diagonal numbers. Weirdly enough, this is my main diagonal, and this one doesn't have a name. I looked it up. Doesn't have a name. Whoa. So 32 minus -14 gives me 46. It's one of the many methods you can use. Doing cofactor expansion for this one wouldn't be that difficult. You have a 0 in row 1. Use it. Okay, so I found my determinant. A inverse equals 1 over 46. Now I need to find my adjoint matrix. Not main. You're not main diagonal. I like the MATLAB notation. My adjoint matrix is actually pretty quick, easy to find. I just find all of my cofactors. Okay, so let me find my cofactors down here. Let me copy my A matrix. Nope, wrong button. Copy. Paste. For my cofactors, it's the same process. We're going to take the element, cross out the row and column it's in, and find the determinant of my remaining numbers. So I have to do this for all of my elements, so I'm not going to cross out any rows or columns right now, just so it's not cluttered. So for C11, if I cross out row 1, column 1, I end up with 1, 5, 3, 3. And then I need my grid. So for a 3 by 3, my grid starts with a plus in the upper left for anything, and then I just alternate as I go along. So this one's going to be a positive of whatever that determinant is. For C12, oh, nope. I'm going to keep it in order. For C12, I have a negative, and then if I cross off row 1, column 2, I end up with -2, 4, 3, and 3. For C13, I end up with a positive, and if I cross off row 1, column 3, I end up with -2, 4, 1, 5. And then I keep going. For row 2, C21, I have a negative. That's my grid. If I cross off row 2, column 1, I end up with 1, 5, -2, 3. For C22, it's a positive in that position in my grid. Cross off row 2, column 2, and I end up with 0, 4, -2, 3. For C23, I end up with a negative. Cross off row 2, column 3. I end up with 0, 1, 4, 5. And then same thing for the last row. So C31, I end up with a positive in my grid. Cross off row 1, column 3. No. row 3, column 1. I end up with 1, 1, negative 2, 3. C3, 2, I end up with a negative, and I cross off row 3, column 2, and I end up with 0, negative 2, negative 2, 3. And then C3, 3, I end up with a positive. Cross off row 3, column 3, and I get 0, negative 2, 1, 1. So now I just have a bunch of 2 by 2 determinants to find. They're all independent of each other, which is nice. So if I do this, I have 3 minus 15, or a negative 12. So that's my first cofactor. This one is going to be negative 6 minus 12. Or negative 18, but this minus sign in front means it's positive 18. Yep. Sorry. And then this one I have negative 10 minus 4, or it ends up being negative 14. Keep going. I have 3 plus 10, or 13. If this minus sign, it becomes a negative 13. There we go. For this one, I have 0 plus 8, or 8. This one I have 0 minus 4, which is negative 4. This minus sign means it becomes positive 4. Down here I have 3 plus 2, or 5. Here I have 0 minus 4, or negative 4. This negative here means it becomes positive 4. And here I have 0 plus 2, or 2. Found all of my nice and easy 2 by 2 determinants. So now what I'm going to do is I'm going to plug them all into my matrix. So C11 becomes negative 12, C12, 18, negative 14, negative 13, 8, 4, 5, 4, 2. I just plug them in their corresponding locations. So here's my conjugate matrix. So I'll call it capital C. My adjoint matrix is going to be the transpose of this. So I take this first row and it becomes my first column. So negative 12, 18, negative 14. Take this second row, it becomes my second column. So it's negative 13, 8, 4, and this third row becomes my third column, 5, 4, 2. You can plug them in directly. You can transpose them directly from your calculations here. And that doesn't matter. Just know that you have to transpose it eventually. Okay, there we go. I found my adjoint matrix. I'm going to copy and paste this beauty. Copy over into my formula. Paste. Okay, now to find my final answer, it's just a basic multiplication of a scalar times a matrix. So my final A inverse is going to be negative 12 over 46, or negative 6 over 23. Then I have negative 13 over 46, 5 over 46, 9 over 23, 4 over 23, 2 over 23, negative 7 over 23, 2 over 23, and 1 over 23. So much easier than doing Gauss-Jordan elimination. Notice I end up with fractions, but it's all the way at the end. I have my determinant that I can pull out. And I just do a bunch of cofactors, a bunch of smaller determinants to figure out. Each of these determinants are independent. It's so much easier to debug this method. So I encourage you, if you have the option to find the inverse of A, use this method. No, it wouldn't be considered wrong if you don't simplify these final fractions. If you left it like this, that would be totally fine. Either of these are fine. Note in MATLAB though, so if we check our answer in MATLAB, A is this one, 0, 1, 2, -2, -2, 1, 3, 4, 5, 3. If you want to check your answers in MATLAB, you would just say inverse of A. And it will give you the fractions if you have format rat. Notice the fractions MATLAB gives you will be simplified, so you can always check your answers that way. But yeah, you can leave it in either form. Okay, now I have A inverse. That's great. Woohoo! Now I can solve for X. So remember, this is our final result. We want to apply this equation in order to solve for X. So I just take A inverse, which this one is much easier to work with because you don't have lots of fractions, you only have one fraction. So you take A inverse and multiply it by B. And when I do that, I'm just gonna copy and paste again. Copy, paste. My B vector looks like this, 6, -7, 13. So I get 1 over 46 times 6 times -12 plus -7 times -13 plus 5 times -13. Second one, 6 times 18 plus 8 times -7 plus 4 times -13. And then -14, or I'll do 6 times -14 plus 4 times -7 plus 2 times -13. When I do that in math, oh brother. I get, 1 over 46, -46. That's nice and convenient. Zero, also nice and convenient. And -138, which I'm hoping is convenient. So when I simplify this one, X equals -1, 0, and -3. There we go. There's my answer. Find A inverse, get B, do that multiplication, we end up with X. So now we have two methods to use in order to find the inverse. Okay. 10 minutes. Okay, the last thing to cover for today is Cramer's rule, which Cramer's rule is, once again, just calculating determinants. But it's another method that we can use to solve for X. It's another method we can use to solve for our answer. And really it just requires calculating a bunch of determinants. So what we do for Cramer's rule is we are going to find the determinant of A, and we are going to find the determinant of a bunch of AKs. Yeah, so if there are 3 unknowns, then there are 3 AKs. If there are 4 unknowns, there are 4 AKs. If there are 5 unknowns, there are 5 AKs, etc. So let me show you how to put those together. So we'll use the same system of equations. I'll just copy and paste it down. Should get the same answer. But let's say this is our system. AX equals B. I already know the determinant of A is 46. I know that because I calculated it up here. Now I need to find the determinant of A1. So this is my first AK. In order to find the determinant of A1, I'm going to take A, and I'm going to replace column 1, so A1, replacing column 1 with my B vector. So I'm going to erase it and replace it with my B vector. So here is 6, negative 7, negative 13. So I can find the determinant of this matrix, which I'll use cofactor expansion. It's going to be along my first row. It's going to be plus 6 times the determinant of this matrix. So 3 minus 15. Minus 1, so my minus comes from here. 1 times the determinant of this matrix. So negative 21 plus 3 times 13, 39. And then plus negative 2 times the determinant of this matrix. Negative 35 plus 13. So if I do that math, it should give me 46, because I know what the answer is. Nope, it does not give me. Come on. So this is negative 12. This is 18. Yeah. And this is 22, negative 22. Yeah, it should be maybe 46. 6 times negative 12 minus 18 minus 2 times negative 22. It's giving me negative 864, which is not what the answer should be. Ah, gosh. Okay, we'll move on. Determinant of A2. Same thing, except now I'm going to replace column 2 of A. 3 times 13. I'm going to replace, so I have A. And I'm replacing column 2 with my B vector. 6, negative 7, negative 13. Probably have a sign wrong somewhere. So I'll use cofactor expansion along row 1, or I'll do column 1. So plus, minus, plus. So I have 0. Woohoo! Don't need to do anything there. Minus negative 2 times my determinant. 6, negative 13, negative 2, 3. Plus 4 times this determinant. 6, negative 7, negative 2, 3. I'll figure it out. So showing all my work, I end up with 2 times 18 minus 26 plus 4 times 18 minus 14. Which this one should give me 0, and it does. So 18 minus 26 is negative 8. And 18 minus 14 gives me 4. So 2 times negative 8 plus 4 times 4 is 0. So this one's 0. That one worked out. And then A3. Same thing. So note A1 replacing row 1. A2 replacing row 2. A3 replacing row 3. So my A matrix Now I'm replacing row 3 or column 3. Sorry, I keep saying row, I mean column. With my b values, 6, -7, -13. So I'll do cofactor expansion along row 1. Redeem myself. So 0, once again, don't have to do anything. Woohoo! -1 times this determinant, -2, 4, -7, -13. Plus 6 times this determinant, -2, 4, 1, 5. So I end up with 0 minus 1 times 23 plus 24 times 7, 28. 28. You ever have those multiplications where you're like, you think it should be so simple, you just can't remember them? I can never remember 7 times 8 for some obscure reason. It's 56, I think. -10 minus 4. 23 plus 28. So here I have -51 plus 6 times -14. I get 135. Dang it. I'm off by 3. Wow, that's why. 26. There we go. This is 54. 138. There we go. Okay, so I did just type something wrong. That's good to know. Like I said, I probably forgot a sign somewhere. Thank you. Okay, so I've got my 4 determinants. Determinant of A, determinant of A1, determinant of A2, determinant of A3. Now, it turns out that my first unknown, so X1 or whatever my first unknown is, it's going to be the determinant of A1 over the determinant of A. So now I just take my answers. -46 over 46 equals -1. There we go. There's my first unknown. Same thing for X2, but now it's going to be A2 over determinant of A, or 0 over 46, or 0. There's my second unknown. And then same thing for my third unknown. Determinant of A3 over determinant of A is going to be 138 over 46, or 3. So there we go. There's my solution. X equals -1, Y equals 0, Z equals 3. So I got the same answers up here. I have a negative. This should be positive somewhere. Once again, I probably forgot a sign somewhere. But I got the same answers. It's just another method we can use in order to solve our system equations. So one reason why we don't use Cramer's rule all the time is it doesn't apply for all situations. Gauss-Jordan elimination and Gauss elimination, we can apply to any system of equations. We just might end up with a system with no solution, one solution, infinite number of solutions. So so we can always use Gauss-Jordan and Gauss elimination for any system of equations, even if we have more unknowns than we have equations. For Cramer's rule, sometimes it's not always easy to find the determinant of something. It's also computationally expensive to find the determinant of something. Which means that if we are writing a program, we don't want to use Cramer's rule in order to solve it. Also, once again, Cramer's rule only applies when our determinant is not equal to 0. when our determinant of A is not equal to 0, which means there is only one unique solution. We will get more into this in 2 weeks, but Cramer's rule sometimes is really nice to use if the determinants are easy to find. Sometimes it's not. I've run into situations where I've tried to solve the same system of equations using all the methods we've learned, and some systems it's really nice when you or some ways it's really easy for some systems, some ways it's really hard for other systems. So Matthew, I made it so that it works out nicely. Generally, not all the time, but generally the systems we give you guys end up with whole numbers. It's not always guaranteed, but we're not gonna give you big fractions. Like the fact that the determinant of A is 46, so we get this inverse with a bunch of like divided by 23s. That is atypical, especially if you're asked to do row operations. For finding the determinant or finding the inverse using the adjoint matrix, though, it's actually not bad at all. But in general, we try to give you systems where there are mostly whole numbers. Okay, so that's Cramer's rule. Just determinants. Find determinant of A, determinant of A1, A2, A3, however many unknowns you have, and then just do your division. That's it for today. Are there any final questions before we head out? Thank you guys for checking my work. I probably just typed something in incorrectly. I'll probably have it fixed by this afternoon or by the next class. But any final questions? Okay, if not, I'm going to jump over to office hours and I will see all of you guys next week. We're getting there. We are almost there. Keep working, keep chugging through, do your programming project, keep moving forward. You got this. Class has 60 people in it. I mean, people watch the videos. If there's only like 12 students, that's fine. You guys ask questions. It's very exciting. If not, they're a loss. Okay, I'll see you guys next week.